In Module 5, we're going to see how can we approximate the probability of failure of a component by doing a linear approximation and assuming that we know the mean vector and covariance matrix for or random variable involved in either in the resistance or solicitation model. So a little recap. So X is going to be our vector of random variable, as I said, involved in resistance or solicitation. So we're going to have access to the joint probability density function to model this vector random variable. G of X is going to be our limit state surface. It's going to be positive in the survival domain, negative in the failure domain, and the frontier where G of X equals 0 is going to be the boundary between the failure and the survival domain. So you can see here the representation for a two-dimensional random vector. This is going to be the joint probability density represented here by contour. This is my domain omega, my failure domain. All the x's, such as my limit state function, is negative. So the problem we're facing is that when we have large dimensional vector of random variable involved in our reliability problem, it's not possible to plot or joint probability density, and integrating in large dimension becomes difficult. So in such a case, we're going to see analytical methods in order to allow to compute the integration required for evaluating the probability of failure. We saw in Module 4, how can we do this numerically using sampling methods. With Module 5, we're going to see how we can do this approximately using analytical methods. The one we're going to see are MCFOSM and FOSM. So where does these methods stand for? So what does it mean MCFOSM and FOSM? So the M stands in MCFOSM for moments. So moment-centered first order second moment. Mean-centered first order second moments. So the moments we saw in the revision module, that the mean is the expected value of my random variable. So it's centered moment of order 0. The centered moment of, moment of order 0. Centered moment of order 2, we're going to have the variance. So it's going to be the expected value of x minus the mean power 2. So these are the moments we're referring to. So knowing the moments, so the mean and the variance, we're going to do a mean-centered first-order approximation using the second moment. So this is what MCFOSM stands for. With FOSM, that we're going to see next, it's basically the same first-order approximation knowing the second moment, but this time our linear first-order approximation is not going to be centered on the mean. It's going to be centered on what we're going to see is our design point. But in both cases, for both methods, what is common is that what is assumed to be known at the beginning is the mean describing my random vector x. Okay, we're not necessarily going to be able to use some arbitrarily marginal distribution. We're just going to assume we know the mean vector and covariance describing this vector. So implicitly, when we make this assumption that we only know the mean vector and covariance matrix, this is analogous to assuming that we're going to model this exclusively by a multivariate Gaussian instead of being able to use all the expressiveness of using the arbitrary marginal distribution that are going to be joined by a copula like the Neff distribution, as we've seen in Module 3. This will come later in Module 6 with the form method. But for now, let's assume that we model or join probability density simply by a multivariate Gaussian. So what we're going to see is, knowing that X here is modeled by its mean vector and covariance matrix, and we assume that Z is our limit state function. So remember when we look at the first concept of safety margin in Module 2, we said that Z equals R minus S, the resistance minus the solicitation. Here in a more general case, we can assume that Z is equal to G of X. Okay, this again, just like R minus S, is going to be positive in the survival domain, negative in the failure domain. And we assume that g of x, in our case, is going to be continuous and is going to be differentiable. So, uh, so here what we want to model with our function is the probability that z is lesser or equal to 0. So in that case, the probability that z is lesser or equal to 0 is the CDF of my the CDF of z. Give me a second. I'm just trying to replace my screen. Okay, now it should be good. So, as I said, sorry, the PF is the probability that z is less or equal to 0. This is equal to the CDF of my z. So basically the CDF of my limit state function outcome. And we saw that if we want to evaluate that CDF in the z space, this is equivalent to transforming our z in the standard normal space U by saying that I want to evaluate that standard normal random variable for a value that is lesser or equal to minus z divided by sigma z, the standard deviation. And this is equivalent to evaluating the standard normal CDF at a value minus beta. So that ratio minus mu z over sigma z is minus beta, my reliability index. And we saw that if u is my standard normal Gaussian random variable, we can go from a z to a u space by saying z minus mu z divided by sigma z, where in this case, I know that my limit separating the failure and the survival is z equals 0. So that's why I want to evaluate this in u equals in minus z over mu z. So if we illustrate this using the PDF on the standard normal space, we have the PDF here. You see, I want to evaluate the probability content, so the area under the curve in the standard normal space at a distance minus beta from the origin. So this is already what we saw in module 2 when we formulated reliability problem, except that now instead of doing it for a specific case where z equal r minus s, I want to do it in a general case where I use my z equal my limit state function. So basically, if we want to evaluate the probability of failure, we just have to find what is this beta. To find the beta, the only thing we need to find is what's going to be the mean value of g of x. Because remember, x is a multivariate quantity, but the output of g of x is a single quantity. So I only need to evaluate what's going to be mu of z or mu of g of x and standard deviation of g of x. So the question we're going to answer with the method we're going to see in Module 5, MCFOSM and FOSM, is how can we estimate both mu z and sigma z using first order approximation. So we're going to see that first that MCFOSM, then we're going to look back at how can we, in a general case, transform a multivariate Gaussian random vector into its standard normal space. Then we're going to extend, we're going to see what are the limitations of that MCFOSM, and we're going to try to extend it with first order second moment. So we're not anymore going to make our linear approximation at the mean. We're going to do it at what we're going to see is the design point. And in order to identify that design point, we're going to see a method that is called iHL-RF. We're going to see that in detail in due time. And finally, we're going to apply it to an example of our bar subject to a tensile load. So that brings us in module 5, which is the first module where we see analytical methods in order to estimate our failure probability. So again, if you see here, this is the old race car. Why? Because this is a method that's going to be extremely fast in contrast with the bulldozer we had with Monte Carlo that can go anywhere, but it's fairly slow. Now we have a method that is fairly fast, but is not the state of the art. But why are we seeing methods that are not the state of the art? Is because understanding MCFOSM and FOSM are prerequisite in order to understand what do we have with state of the art methods such as form and SORM that we're going to see next. So let's start with MCFOSM. So how is it defined? How is it formulated? And let's make an applied example in order to see what are the strength and limitation of this approach. So in terms of naming, MCFOSM means mean-centered first order second moment. How does it work? We're going to approximate g of x, or limit state function, at the expected value. This is what we saw in the revision module for probability. If we have nonlinear function of Gaussian random variable, if we want to propagate that input uncertainty in x to evaluate the PDF for the output, we saw that one approximation would be to linearize our function, in this case our nonlinear function, at the expected value mx. So to do this, using the same thing we saw in the revision module, we can approximate that general nonlinear function by a plane. So in this plane, we're going to approximate this plane at the expected value mx. So the formula that's going to result from this first order Taylor series approximation is going to be the function evaluated at the mean vector plus the gradient of my nonlinear function evaluated at the mean vector times x minus its mean value. So knowing this, I can say that the mean for the output of that linearized plane is simply going to be g of mx. The standard deviation or the variance of z, so the output of my linearized function, is going to be, in this case, simply the gradient of m of x times covariance of x times gradient transpose. So this is going to be a simple analytical expression because I have now, instead of having my full nonlinear function, I have that first order Taylor series expansion for which we saw that the linear function or affine function of Gaussian random variable gives me those closed form moments. Where, remember, that gradient vector is the partial derivative of my limit state function evaluated for each of my input variable, and I evaluate these partial derivative at a specific point at the mean value. So knowing these two moments, so mu z and sigma z, which is equivalent to mu of g of x, sigma a variance of g of x, I can evaluate or approximate my beta with the MCFOSM method as the ratio between the mean value and the standard deviation, so the square root of what I have here. And this is the definition of my MCFOSM beta. This is very easy. This is super practical to apply. It doesn't involve much implementation, but the limitation here is that we're going to see that the result and the quality of our approximation depends on the formulation of our limit state function. So let's go back to our classic example of a bar subject to a tensile force. So the force is R, which is modeled here by the dimension of my bar squared to obtain the area times f of y, the limit state, the tensile strength. So in this case, we're going to model D and S, the tensile force applied, as random variable. So the mean of D is 10, standard deviation is 2, the mean of the solicitation is 15, standard deviation is 5. My limit state, my limit strength is something deterministic, 300 megapascal, and I'm going to assume that the dimension and solicitation are independent from one to another. So here I can formulate using this solicitation that is directly available and resistance model, two different limit state functions that are both admissible. First one could be R minus S, the classic one. A second one could be 1 minus S over R. So keep in mind, if S is larger than R, that's going to give me something larger than 1. 1 minus something larger than 1 is going to give me something negative. If R is greater than S, it's going to give something smaller than 1. 1 minus smaller than 1 is going to give me something positive. So both satisfy the criteria of being continuous, differentiable, and negative in the failure domain, positive in the survival domain. So both are admissible limit state function. We can plot both here on these graphs. Both have the same x1, x2, x1 being D, x2 being S. And we have two surface representing G1 and in this case G2. So the black point is the mean, m of x, so 10 and 15. And although both shape for the curves are different, here the purple line representing the limit state surface, so g of x equals 0, so the intersection between my limit state function and the plane g equals 0, these purple curve are exactly the same in both cases, okay? Because to be an admissible limit state function, both must describe the same failure and survival domain. But outside of this purple curve, both curves looks different. And what we're going to see is that this is problematic for MCFOSM, okay? Because in both cases, we're not going to get the same estimate for beta or reliability index. So let's start with our first limit state function. So R minus S, so D squared Fy minus S. So in this case, we have the same mean vector, the same covariance matrix. And we're going to look at the first solution for our G1. So mu z is going to be the evaluation of our limit state function at the mean. So it's going to be 10 square times f of y. So I evaluate my limit state function with d at its mean value. So 10 minus 15 is going to give me 15. So we can evaluate the gradient for my first function. So I first differentiate with respect to d. It's going to give me 2x1, so 2dfy. We differentiate with respect to s. It's going to give me minus 1. If I evaluate this at the expected value, that's going to give me 6 and minus 1. Then my variance is going to be my gradient vector I just computed here times my covariance matrix times gradient transpose. If I make the numerical calculation, that's going to give me 13 square for the variance. So my beta, my reliability index, evaluated by MCFOSM, is going to be the ratio between that 15 and 13. 15 over 13 is 1.15. Okay, let's keep that in mind. This is what we obtain if we use the first limit state function. If we use the second limit, and here if we want to compute the probability of function, we simply evaluate the standard normal CDF for minus beta. So for minus 1.15, we would get 12%. If we now evaluate the same solution with the second limit state function, this is also an admissible one. In that case, we compute the mean, we evaluate the limit state function at the expected value. So 1 over 15 divided by 10 squared times f of y. That's now going to give me 0.5 for the mean. The gradient, I differentiate this function first with respect to d. That's going to give me this term. We then differentiate with respect to s. That's going to give me this term. If we evaluate numerically by replacing the value at the expected value, I'm going to get 0.1 and minus 0.03. Then the variance is going to be that gradient, sigma x gradient transpose. If we evaluate numerically, at the standard deviation is going to be 0.21. So 0.5 divided by 0.21 should give me my reliability index. So in this case, that's going to give me 1.92. Remember, previously with the G1, we got 1.15. So there's a big discrepancy between the reliability index obtained with the first and second limit state function. So we can see why does this happen. So what we're doing when we're doing our first order Taylor series expansion, the real g of x, so either g1 on the left or g2 on the right, are these nonlinear plane. And what I do with my first order Taylor series approximation is I'm going to replace that nonlinear function by a plane. So the plane is the kind of black grid we can see here. So the first one on the left, we can see that the plane has been kind of fitted at the point that is here in black, the mean value. The black plane that we have for G2 is fitted at this point, which represent the mean value for my second function. So in this case, you can see that even if the purple line, which is the limited state surface, is the same in both cases, the blue one, which represent the linearized limit state surface, is different in both cases. So you see that the part that is on the left here represent the failure domain. So in this case, we're going to overestimate the probability of failure. In this case, we're going to underestimate the probability of failure compared to the true limit state surface. So if we look at the true probability of failure, which should be 0.08. In this case, if we use the MCFOSM, we're going to get 0.12 for the first one, and we're going to get 0.027. So we really overestimated here compared to 0.8. We're going to underestimate it here compared to 0.8, 0.08, sorry. So we can see it as well if we reorient it here as a contour. So the same thing here seen from the top. We cannot see the surface anymore, but we can see the failure domain, survival domain, failure domain, survival domain. Both are delimited by this exact same boundary. And we can see how here with my first limit state function, I'm going to overestimate because I'm going to consider all the area here that is not in the pink area here. I'm going to underestimate everything in the intersection there. Okay, so we want to extend with FOSM with a method that's not going to be sensitive like this one here to the choice of the limit state function. And to do this, the first thing we need to see is review the transformation from the original space X, which is going to be a Gaussian, to the standard normal space U. So how can we perform that transformation? And what is the interpretation of our beta or reliability index in the standard normal space. And how can we use this interpretation to compute the failure probability? So again, remember that U is going to be a vector of n standard normal random variable. It can be expressed by this joint PDF. So the contours of this standard normal space are going to be spherical, or in that two-dimensional case, circular, and they're going to be centered at the origin. So no matter what cut I'm going to do, I'm going to obtain a shape that looks like a Gaussian. And in all direction, the probability decrease exponentially with an increment in the square of the distance with respect to the origin. So this is the standard properties of that standard normal space. And the fact that I have circular contours or spherical contour will allow me to take advantage of that rotational symmetry that I have. Because in this case, if I have a one-dimensional here standard normal random variable, we said that the probability of failure is located at a distance minus beta from my origin. But what we can see if we extend this to a two-dimensional domain, so imagine I have u1, u2. In that case, I can define here a plane, and the probability defined by the distance between the origin and this plane, so the length beta here, the probability that I have in this 1D space is equal to the probability that I have in this two-dimensional space. So the only thing that matters, either in 1D, 2D, 100 dimension, is only the distance between the origin and a plane. So at the end, if we can find this beta, whether we're in a 1 or 100 dimensional domain, we're going to be able to evaluate our probability of failure. So here in summary, the probability of failure or reliability index is completely defined simply by the distance between our origin and that limit state surface. So this is what we're going to be aiming at finding and estimating as accurately as possible. So to do this, we first need to review how do we transform from a random variable, so normal random variable x, to the standard normal space u. So if x is multivariate Gaussian, we can do the transformation from x to u using this transformation. So x minus its mean times the inverse of the standard deviation matrix, a square matrix with only the standard deviation on the main diagonal, times the Cholesky decomposition of the correlation matrix. Okay, this is the same thing we saw again in the previous module. We can have the reverse transformation, so from u to x. So u times that Cholesky decomposition times d plus mx, simply the reverse of this equation. Where the covariance matrix is standard deviation matrix, correlation matrix times standard deviation matrix. We have here that square matrix with diagonal on the main, with standard deviation on the main diagonal. And L is the Cholesky decomposition, so a lower triangular matrix, which is the decomposition of my correlation matrix. So what we can say is that since there's a one-to-one mapping between the X space and the U space, if I know U and I know X, G of U should be equal. It means that the limit state function evaluated for a given x should take the same value that that limit state function evaluated in the u space. So that means that if I want to evaluate g of u, I'm simply going to evaluate g of my transformation from u to x. Okay, so I can now express my limit state function in terms of u if I want to. And keep in mind, as I said earlier, that L is going to be a lower triangular matrix for my Cholesky decomposition. So what is the interpretation of my beta, my reliability index, in the standard normal space? So given that I have g of x, which is going to be my limit state function, that I'm now going to want to approximate by a linear function or an affine function. So I'm going to have a0, a constant, plus the sum of ai xi. I can represent this in a vector form as a0 plus a vector a times x, where a is my n-dimensional vector corresponding to the number of random variable I have in x. So in that case, I still have the same two transformation from x to u and u to x that I defined earlier. And I can define g of u, which is equal to g of x, by simply using that same relationship and replacing x by its relationship x plus dxlu. So this is what I'm going to replace inside the parentheses here. And I can regroup these terms by multiplying A transpose into my parentheses. And I'm going to regroup in B0 all the terms that are constant. And I'm going to regroup in BT the coefficient in front of my standard normal random vector U. So I'm going to have B0 and B transpose. So I can rewrite in a matrix form G of U equals B0, which is all these coefficients here, plus B transpose, what I have my three terms here, times U, my standard normal random vector. And given that U is a multivariate standard normal random vector, mean vector 0 covariance identity, I can model or I can compute directly what is going to be the mean for G of U. So the expected value of G of U is going to be what? Is going to be my constant part. So it's going to be simply my B0. If I want to compute what's going to be my variance for G of U, so I'm going to have my B transpose times the covariance for U is going to be identity times B. So B transpose times identity times B is going to be the square for the norm or the length of my vector B. So at the end, given I have these two quantities, I can model my beta, my reliability index, as again, always the same thing, the ratio between mu G, so B0 divided by the norm of B. So we can interpret beta as being simply, again, the distance between the origin and the limit state surface. Okay, so the surface for which B0 plus B transpose U equal 0. Okay, so the only thing we need is that if we can evaluate what is going to be in that first order Taylor series expansion, B0 and B transpose, I can easily calculate these things. So B0 is directly there. If I compute the length of that vector, I'm going to get the denominator there. So this is going to be the essence between all the analytical methods we're going to see. So knowing that we have omega, which is our failure domain. So in the standard normal space, this is the pink area. So all the values u, such as g of u is lesser or equal to 0. And we're going to assume that this the failure domain is bounded by a plane, or in a larger dimension by a hyperplane. We can say that the probability that u belong to this failure domain, from a kind of explicit standpoint, we can express it as the integral over the joint standard normal PDF over all the domain omega. But we know that this probability contained here is directly evaluated by the standard normal CDF in one dimension at minus beta. Okay, so we saw that this from the property of the rotational symmetry of the standard normal space. And this evaluation in one dimensional is equivalent to the PF we want to define in our original X space. So this is a simplification that we're going to use in order to be able to approximate in a quick and efficient way, or beta that will tell us what is the probability of failure for our component. And this is behind what is in FOSM, first order second moment method. So what we're going to do first is that we're going to go, we have an original space defined by a multivariate Gaussian with or without some dependency between my dimension. I'm going to transform this using my transformation function we just saw in the standard normal space. And I'm going to create my first order Taylor series approximation in that standard normal space. And I'm not going to do it at the expected value anymore, that approximation. I'm going to do it at what we're going to call U star, my design point. Okay, and then once I'm going to have this, I'm going to be able to compute my beta. Once I know my beta, I'm going to be able to compute the probability content in that kind of sign area defined by this plane. And this probability of failure will correspond to the PF I'm looking for in the original space. So let's look in more detail in the FOSM method. So I have my standard normal space U1, U2 in 2-dimension. I have my limit state surface in purple here. So I'm going to find my relationship between my original space X and my standard normal space using this same formulation we're seeing over and over again. And if we use this relationship, I can see that my origin in the standard normal space correspond to the mean value in the original space. So when we were using MCFOSM, what we were doing is that we were linearizing. So we were applying our first order Taylor series expansion at the origin in the standard normal space because we're evaluating that at the mean value in the original space. But what we want is evaluating this at the origin, where it's a good approximation here, but it might not be a good approximation there, where we're interested in correctly separating the failure and the survival domain. So we can see here as an example, we can have a very crude approximation of what should be my limit state surface. So instead, and this is what MCFOSM does, instead of linearizing there at the origin, we're now going to linearize at a point U that is located on the limit state surface. But not all points on the limited surface are equivalent. Like this point is good, but this point is better. Why? Because it is closer or it is higher in the joint PDF in the standard normal space, meaning it is going to be closer to the origin. So we're going to define U star as our design point, the one that has the highest probability of failure in my standard normal space. So this FOSM method, as a main advantage, is that we're going to be invariant with respect to the choice of our limit state function. So if we use the two different limit state function we defined earlier, we're going to get exactly the same beta. So to do this first, we're going to transform our original limit state function into the standard normal space using the same transformation function we saw earlier. Then we're going to linearize the limit state function defined in the standard normal space. We're going to make that linearization not at the origin, but at the most failure point U star. And this is what we're going to call our design point. So to do this, first, we're going to say that, okay, G of U, how am I going to linearize my limit state function in the standard normal space? I can express this as the same way as before. So G of U star plus the gradient of U star times U minus U star. So in this case, if I'm on my limit state surface, I know that G of U star is going to be equal to 0. Okay, easy. So I'm only going to be left with what's on the right of the plus. So if I distribute the gradient inside the parentheses, I'm going to have the gradient times my random variable plus and minus gradient times U star. Where in this case, how do I obtain my gradient for G of U? I have access to my gradient of G of X, but how do I obtain it? So gradient of G of U is the derivative of G with respect to U. So dg du is dg dx, dx du. Okay, by using the chain rule of derivation, I can obtain the gradient of g with respect to u as the gradient of g with respect to x times the derivative of x with respect to u. And I have easily access to these things because that Jacobian, the derivative of x with respect to u, is simply the standard deviation matrix times the Cholesky decomposition. And these are simply the coefficient in my transformation relation between the original and the standard normal space. So the mean for G of U is going to be minus the gradient vector evaluated at my design point times my design point itself. So how do I obtain this? It's simply the constant part that I have here in my linearized limit state function. The variance is going to be gradient times identity matrix times gradient transpose. This is what I have here. And this here represents the square for the norm of the gradient. So the length of my gradient vector. So if I divide these two quantities, mean divided by the square root of the variance, that's going to give me my approximated beta using the FOSM method. So I'm going to get, if I divide the mean by the gradient, is going to be minus the gradient divided by its norm times U star. Where here, we're going to have a quantity that we're going to name alpha. So you can see that alpha is that little blue vector that we can place, in this case, at U star, and that's going to point towards the failure domain. So if we regroup all these terms into alpha, we can say that beta is simply going to be alpha times U star. And this alpha is going to be my normalized negative gradient vector. So it's a vector of length 1 that, if placed at U star, points towards the failure domain. And the particularity is that this is perpendicular to my limit state surface that is in cyan here. And it's going to point, as I said, into the failure domain always. So alpha, the definition is going to be the gradient vector evaluated at u star divided by the length of the gradient. So it's going to be a gradient of unit length, and it's going to be of negative sign. And U star is going to be my most likely failure point, or my design point, as we're going to call it. And we can always find my design point, U star, by saying it's going to be beta times alpha transpose. So alpha is my gradient vector of length 1 here. And this is equivalent to say that my design point is the point or the coordinates u that minimize this, so that has the shortest distance to the origin, such that the value of the limit state function is 0. So it's the point that is closest to the origin while being on the limit state surface. And we can find this point either through optimization or by doing beta times alpha transpose. So the next question we need to answer is, how do we obtain that U star? And we're going to obtain this through the iHL-RF method. So there's no closed form analytical method to find U star in one single step. So instead, what was developed is the iHL-RF algorithm. This is an iterative algorithm that allows us to recursively find the optimal design point. So to do this, let's go back to our formulation of the first order Taylor series expansion for our limit state function in the standard normal space. So at the first iteration of our iHL-RF recursion, we're going to say that we can start, for instance, at the expected value in the standard normal space. So if I want to evaluate this, before we said g of u star was 0 because it was a limited function. But if we start at the mean value initially, we're not going to be at a point where g of u is 0. So we cannot remove it as we did before. So what we're going to do is that we're going to expand this gradient into the parentheses. So we're going to multiply it into, and we're going to regroup all the terms that are constant. So that's going to be now the mean of GU. And then we're going to say that beta is the mean of GU divided by the standard deviation. So gradient times identity type gradient transpose, square root of all this. So if we expand, knowing that the numerator is for the mean is this term here, and we can obtain this relation. If I then separate the denominator on two different terms, we're going to have the gradient divided by the norm of the gradient plus alpha times ui, because the gradient divided by its norm, so its length, is going to be the unit length vector alpha. So I can say that my next design point, if I start, say, at the origin, is going to be the multiplication of beta. So the beta that I've approximated here times alpha. So if I explicitly represent the term here times itself alpha, I'm going to get this new term. So I can approximate what should be my new linearization point, u, by saying I'm going to evaluate these terms, where g of ui I can easily do. The gradient of g of ui is going to be the gradient of x times the Jacobian of x to u. So it's going to be d times L. And alpha is going to be my gradient divided by its norm. I have access to this. Ui is my current design point. And alpha, I have already evaluated. I have all quantities to compute my new design point. And I'm going to keep repeating this successively. So if we start at iteration 1, we're at the origin here. Okay, I'm going to evaluate my gradient of my g of u at the origin, and I'm going to obtain my vector alpha by normalizing it. So the gradient divided by the length of my vector is going to give my vector alpha. Then if I do my evaluate my beta using this relation we derived earlier, we're going to get an approximation for my beta. And this would be my, or approximate limit state surface at the first iteration. It's good, but it's not great. We can do better. So we're going to go with a second iteration where instead of linearizing at the origin, we're going to linearize at this new point u2. So if we do this, we're going to recompute the gradient, and we're going to find a new design point where we're much closer to the limit state surface. And we see that our approximation of the limit state surface in cyan here is very close to the reality. And if we do a third point, we see that we marginally move from the second point, and we can say that here we deem to have converged. We have found our design point, and we're going to minimize the approximation error by doing our first Taylor series expansion at this point that is located on the limit state surface that is the closest to the origin. But there's a little caveat with this iterative method, iHL-RF, is that for this type of recursive methods, we can diverge if the step between two consecutive iteration is too large. And we can illustrate it with what happened typically when we try to find the value of a function equals 0 using iterative methods such as Newton-Raphson. So these methods say that if I start from x0, I want to find a place where this function equals 0. So this intersection here. But to do this, if I use a linear approximation of my function to find it equals 0, I'm going to find this function, I'm going to approximate here, and in such a case, I would converge the correct root of my function with it is equal to 0. However, for other cases, such as this one, if I evaluate my first order approximation there, it's going to bring me there, it's going to bring me there, but there the derivative bring me somewhere that is not towards my root. So what I want to illustrate with this example is that in these iterative approach that rely on linear approximation to find specific value of functions, if the difference in two successive evaluation is too large, it's possible that we may diverge and not converge to the right solution we're looking for. So a solution to prevent this from happening is to say that my next design point is going to be my current design point plus a lambda factor times a direction of search, where simply the direction of search is going to be the difference between the solution that is directly computed time by multiplying beta times alpha minus the current design point, where lambda is going to be a factor between 0 and 1. 1 meaning business as usual, we don't apply any correction, and a factor lesser than 1 is going to slow down my learning. So in order to make sure we don't diverge, we can evaluate this merit function. So we say that if the new point proposed by ui plus lambda I di, so my new point ui plus 1, if it has a merit function value that is lower than the merit function for the ui point, I'm going to accept to move with the current lambda factor. If not, I'm going to have to reduce the lambda factor to move by a factor that's less than 1. So my merit factor is takes the following form. So the first part will measure what is the distance between the origin and the linearization point u. So we want this quantity to be as small as possible. Okay, so we want from iteration to iteration for this distance to get smaller. And the second thing is we want g of u in absolute value to be as small as possible. So we want to be as small as possible to our limit state. We want to be as close as possible to our limit state surface so that this value is close to 0. And we need to satisfy this with a constant c that is defined to be greater than the norm of ui divided by norm of the gradient. So we can select any c that will satisfy that criteria. And if we satisfy that criteria, we're going to be able to guarantee that if we satisfy this constraint that my new design point leads to a merit function that is smaller than the previous point, I'm not going to diverge. We could theoretically find an optimal lambda value, so the argument lambda that minimize my merit function, but the problem, this becomes itself a complex optimization problem. So typically we're not going to go in such a complex optimization thing. We're simply going to say we're going to try with lambda equal 1 to satisfy this. If it doesn't, we're going to divide, say, lambda by 2. And we're going to recursively do this until we satisfy the criteria that my merit function is reduced between two consecutive iterations. So at the end, when do we stop doing these iterations? We need two convergence criteria. The first one is that the ratio between my current evaluation of my limit state function and the one that I add at the origin is smaller than a value epsilon. Okay, we need to do this because we don't only want to evaluate g of ui smaller than epsilon, because we can multiply our limit state function by 1,000,000 and it's still a valid limit state function. Okay, so we want to look at the ratio rather than the absolute value of the limit state function itself to be independent of some possible coefficient we would multiply onto our limit state function. The second one is that the distance between two consecutive linearization points must be smaller than the second convergence criteria, epsilon 2. In practice, we can take for epsilon 1 and epsilon 2 something that is in the order of 10 to the minus 3. So let's apply this to an example. So we have again our bar subject with a resistance R subject to a tensile force S. We're going to model R of X as D squared times F of Y. F of Y is given. And G of X is going to be R of X minus S. So I have my X vector, which is X1 is D, X2 is S. I have my mean vector and covariance matrix. I have this is my standard deviation matrix. My correlation matrix is a diagonal matrix because both the variable are independent. If I do my Cholesky decomposition of that R, this is still an identity matrix. I can evaluate my gradient vector. So derivative of this with respect to D is going to give me 2x1, so 2d f of y. Derivative with respect to S is going to give me simply minus 1. So I will need my Jacobian to do my transformation and to evaluate my gradient from x to u and u to x. So in this case, it's going to be the Jacobian from u to x is going to be the inverse of my Cholesky decomposition times the inverse of my standard deviation matrix. This is my number. If I wanted to obtain my Jacobian from x to u, I simply invert what I have there, 2 and 5. So my transformation from x to u involve a Jacobian between u to x. So it's going to be that matrix I already computed here times x minus the mean vector. So this is going to allow me to go from my x space to my u space. If I want to do the reverse, to go from u to x, so it's going to be my Jacobian gxu, already computed here, times u plus my mean vector. So if we want to go into the iHL-RF recursion sequentially, the first step is going to be to initialize the first linearization point. We typically initialize at the mean vector mx. That's going to correspond to the origin in the standard normal space. Then we evaluate g of ui. So we evaluate for the point 0 in the standard normal space. This is mx at the original space. I evaluate g of xi, g of end of x. So if I evaluate numerically, that's going to give me 15. The gradient of my limit state function in the u space is going to be the gradient evaluated at the current design point, in this case m of x, times the Jacobian of x towards u. So in that case, if I evaluate this numerically, it's going to give me 12 and minus 5 for my gradient in the standard normal space. I can evaluate my gradient alpha. So I take the gradient I've computed here and divide by the length of the gradient, add a negative sign. That's going to give me minus 0.92, 0.38. I can compute my direction in which I want to search for my next point u2 as being beta times alpha minus the current point. Current point is 0. So beta I is going to be that calculation times alpha that I already have here. If I evaluate that direction of search, it's going to be minus 1.07 and 0.44. Then I'm going to evaluate what should be the next point. ui or u0 is 0. u1 is going to be u0. So 0 plus lambda. We're going to start with lambda 0 equal 1 times my direction of search. Same thing as I had before. Then we need to evaluate, did I improve from the point 0 to the point 1? So I evaluate my merit function for the 2 point u0 and u1. I can compute that criteria that I need to satisfy. That criteria gives me 0. I choose a coefficient c that is equal to 10. So 10 is the greater than 0. I'm all good. In this case, my merit function at 1 is 14. At 0, it was 150. I decrease my merit function. I'm better. Perfect. I can carry on with my lambda equal 1. If it wouldn't be the case, I would have need to say, I'm going to reduce my lambda by a factor 2 and recompute until I satisfy that my merit function decreases over 2 consecutive steps. So now I have my new design point, which is going to be this one. I restart with the step number 2, and I redo my transformation. So what the point that's minus 1.07 and 0.44 in the standard normal space correspond to what point in the original space? We can evaluate using this relationship, 7.87, 17.22. And we can see that here in 3 iteration, we can find our u star, so our design point. That corresponds to a beta of 1.28. We can have evaluate our alpha at our normalized gradient vector. And we have our design point in the original space that is equal to those coordinates in the standard normal space to these coordinates. And if we evaluate with this beta or probability of failure, the real one is 0.08, the one with FOSM is 0.10. And remember with MCFOSM, we had 0.12. So we see that we're closer to the reality than we were before, because now we're really careful in evaluating our limit state surface exactly on the true limit state surface itself. Okay, so we're doing our Taylor series expansion for a limit state function directly on the limit state surface, and that minimizes the approximation error when computing or probability of failure or beta. So this was for lambda equal 1. Let's look what happened with smaller lambdas. So if we look first at the same example, so we can see here, we can start that same example we saw before. So we have here the X space, original space. We have the standard normal space. So you can see here my limit state function for the X space, original, and standard normal space. At my first iteration, all the quantities I evaluated with you in the previous example. So then I can make a second step. So going from the original, I have my new point at step 1. We see our limit state function now is evaluated there. And we see that already at point 3, we converge, we pass or both convergence criteria, and we can stop, we can evaluate our probability of failure using this approximation. And now what I wanted to look at with you is that this was if we use a lambda equal 1. But if we use a smaller lambda, say 0.1, what is this going to look like? So we can see that instead of moving a full step at each iteration, I'm going to move by a step of say 0.1. So in that case, I'm going to move very slowly from step to step. I'm going to reach the same final point, but I'm going to need way many more evaluation of my limit state function. In this case, I'm already at 30 iteration to converge. So theoretically, you can always start with lambda equal 1, and you decrease only if needed because you don't satisfy the merit function decrease over 2 consecutive steps. So I'm going to stop here. I'm at 6th iteration. I haven't converged yet. So if we look at the case where we could do the same thing, but this time with some correlation between my two random variable, we can see that we have correlation in the original space, but whenever we work to evaluate our limit state function in the standard normal space, we always work in an independent standard normal space. So you can see that in this case, with my correlation coefficient equals 0, I add a probability of failure of 0.10. Now, if I modify my correlation, we can see that even if I don't have any correlation, in this case, in the standard normal space, it changes my probability of failure. It is now 0.05. And why, if I don't have correlation here, I can have a change in the probability of failure is because the correlation is taken into account when transforming from my original space to the standard normal space through that Cholesky decomposition in my L matrix. So in summary, the MCFOSM and FOSM methods are based on the principle that we only have access to the mean vector and covariance matrix for my random vector. So that implicitly makes the assumption that I model my joint probability density by a Gaussian random variable. In both cases, for MCFOSM and FOSM, might not be a very accurate representation of my probability of failure because it's always going to approximate the limit state surface by only a plane. So if my true limit state surface is linear, so it's going to be a very close approximation to the reality, but if it's nonlinear, such as this, I can either underestimate my probability of failure or overestimate it. So whenever we're going to have strongly nonlinear limit state surface, I might not provide accurate representation of probability of failure using both methods. Regarding MCFOSM, we can have severe limitation in a sense where, depending on our formulation of g of x, we can have two radically different probability of failure or two radically different reliability indexes. So that's why we're not going to ever linearize at the mean. We're instead always going to linearize at the limit state function, a point that is on the limit state surface that is closest to the origin. So that was what we had to see with the FOSM, so that old race car. So a very fast method compared to Monte Carlo, but that's not yet the state of the art. And the main limitation here is that we only assume that the joint probability density is a multivariate Gaussian, whereas in practice, if we want to correctly model the far tail of our distributions, we need to take into account the knowledge of each marginal random variable as well as their joint density that will be modeled by a NetTaf distribution. And this is the key these are the key elements behind the form method that are going to be seen in module 6.